Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences students, and the paper is on applied electronics. And in the lectures which we have been seeing under unit 2, so far we have seen positive ray analysis, which are nothing but protons, and in this lecture we will start with photoelectricity. So, the contents are as follows: discovery of the photoelectric effect, critical frequency for ejection of the electrons, loss of photoelectric emission, Einstein's photoelectric equation. And what are photoelectrons, or what is photoelectricity? The word photo means, what does it mean? Photo means light. So, light incident on metals were found to eject electrons. Suppose I have a metal, and when light is falling, you got a source here, a bright light in front of me. When light is falling, then the electrons will be coming out of the metal, and this effect is known as the photoelectric effect. This is what is shown in the slide. You see here, light is incident on a metal piece, you got a metal piece. And what is a metal? You all know by now, metal consists of free electrons, and I am showing here the circles with the minus sign. They are the electrons which are present in all metals. You know, metals have metallic bonding. What do you mean by metallic bonding? The free electrons roaming here and there within the metal, it leads to metallic bonding. And the important point is, in all metals you have got free electrons, and when light is incident on a metal piece, these free electrons will come out of the metal, and the electrons are coming out. This effect was observed by Hertz, and so the credit goes to Hertz, who found the photoelectric effect. And almost all the effects, maybe the Röntgen's discovery of the X-rays or the discovery of the electron, and many other phenomena in physics, they are all accidental. And so, this is again an accidental discovery which was made by Hertz. And so, light incident on a metal piece will eject electrons, the electrons are coming out, right. So, you may ask the question whether this phenomenon will be exhibited by all the metals, right, whether all metals will exhibit. Now, let me tell you, you take cesium metal, right, you look at a periodic table, you find out where is cesium. I tell you, there are reasons why I am talking about cesium. The electrons are very loosely bound in cesium. Therefore, cesium when exposed to sunlight, you need not have a light of any particular frequency. You can use the sunlight. You place cesium metal plate in sunlight, then the electrons will be coming out. So, the energy possessed by the light coming from sun or sun rays can eject electrons. So, this is a so called photoelectric effect, which can be easily observed in a metal like cesium, or the answer to a question whether all metals will exhibit this effect. I will come to that. The point is it is better to make use of ultraviolet rays. What do you know about ultraviolet rays? How do you compare ultraviolet rays with respect to the light that I have here? This is the visible light, right. I am surrounded by lots of lamps which I can see, and you know the visible light ranges from 4000 angstroms to 7000 angstroms, and you know in the electromagnetic spectrum where you find the ultraviolet light. Ultraviolet light means nearer the violet, it has got a higher frequency, higher energy and so on. So, the point is the ultraviolet rays which are incident on a metal plate will obviously expel electrons, will be able to eject electrons from the metal. I told you that when light is incident on a metal plate, the electrons are coming out. So, also here when ultraviolet light is made to be incident on a metal plate, electrons will be coming out. You know electrons are negatively charged particles, and so you got a positive polarity here, and so this plate is positive, the plate, this is a plate or a curved surface. So, the electrons will be accelerated or will be attracted towards the positive plate, resulting in a current or a deflection that will be shown in the galvanometer. So, the point is all metals exposed to ultraviolet beam, right, ultraviolet rays will be able to eject electrons, but as I told you, cesium, which has got the least electronegativity or it has got loosely bound electrons, it will be able to eject electrons even when it is exposed to sunlight, whose energy is much lesser compared to the ultraviolet beam. Okay. Anyway, the ultraviolet rays will be able to eject electrons from all metals, and the electrons will be attracted towards the cathode and the plate here. The plate is positively charged. Okay. So, the photoelectric effect is studied with the help of the experimental setup which I showed just now. You can have a hollow cylinder, a plate, whatever be the thing, you can have a quartz window and the plate is connected to the negative and the end of the hollow cylinder is connected and so on. Anyway, the point is a galvanometer which is used in the circuit, when the electrons are coming out, the circuit is getting closed, and so you can see a deflection, the circuit is getting closed. Okay, before your electrons are coming, the circuit is not closed or a current does not flow. Now, a photoelectric current will be flowing in the circuit. There will be a current. What is current? Current is nothing but the flow of electrons, and so you have get electrons coming out of the metal plate. So, current will flow. So, the photoelectric current will be produced whenever ultraviolet beam is incident on metals. You can have any metal. Okay. So, the galvanometer shows a deflection and thus photoelectric current is produced within the circuit. The effect of light of a range of frequencies was studied. So, in order to understand this phenomenon, you make use of radiation of all possible wavelengths or frequencies, as I will be showing, and you ask the question whether all radiations will be able to eject electrons. So, in this discussion I should before I go to the laws of photoelectric emission, which are very important, the experimental observations which were the results of the experimental observations are very important. Let me now pose the question or show an interesting slide. You have the energy of the beam. Supposing you have light to be incident on a metal like potassium, right. You have got a metal like potassium and you have a beam whose wavelength is 700 nanometers. What do you mean by 700 nanometers? It is 7000 angstrom unit, right. When you have 7000 angstrom unit, you have the relation. I should not tell you about this relation at this point of time, because it was Einstein who made use of quantum theoretical ideas, and he introduced the quantum theoretical ideas to explain this phenomenon. However, I should tell that 700 nanometers, when it is converted into the energy, it corresponds to 1.77 electron volt. Let me again tell you, when the metal plate is made to be incident on by a beam of wavelength 7000 angstrom unit, the energy associated is 1.77 eV. Then the important point is no electrons are coming out, there will be no photoelectric effect, that is important. So, all light beam will not be able to produce photoelectric effect, right. Remember, all the light beam, any you cannot take any light beam and make it to fall on a metal plate and expect the electrons to come out, or the photoelectric effect cannot be observed. So, a metal plate like potassium, when it is exposed to light of wavelength 7000 angstrom unit, you do not have electrons, electrons will not be coming, electrons will refuse to come. There are free electrons in every metal, potassium will have free electrons, but electrons will not be coming out. On the other hand, you go to from 700 nanometer wavelength, you reduce the wavelength. You are reducing the wavelength means what? You have B is equal to n lambda, lambda is decreased means frequency should be increased. When you increase the frequency, or when you increase the energy of the beam, then from 700 nanometer you go to 550 nanometer, then that corresponds to 2.25 eV, then you find that electrons are coming out, right. And you have what is called potassium, the needed energy for the electron to be ejected is 2 electron volt. Now, this energy here is 2.25, therefore, this light beam is able to eject the electron, and the ejected electron will be coming with a velocity which is 2.96 into 10 to the power of 5 meter per second. Okay. So, the point is, a beam having 7000 angstrom as the wavelength will not be able to eject the electron. On the other hand, the reduced wavelength 550 nanometer or 5500 angstrom having a energy 2.25 eV, it is able to eject the electron. The reason being, the energy needed to eject the electron is 2 eV. What is the energy needed? In all metals you have got free electrons, but the electrons will not be coming out of their own. You do not have electrons coming out of their own. You know, when you heat a metal, electrons will be coming out, it is called a thermionic emission, or you can expose it to some light, electrons will be coming out, that is called a photoelectric effect, or you talk of field emission, cold emission, etc. Those things mean that electrons are bound to the metal, like electron is bound to the proton, the hydrogen atom with 13.6 eV, electron is bound to the atom, electron is bound to the molecule, electrons are bound to metals. So, energy should be given. So, for potassium the energy to be given is 2 electron volt, that the energy needed to remove the electron. So, with 5500 angstrom energy, the velocity of the electron will be 2.96 into 10 to the power 5 meter per second. Now, if you reduce the wavelength still further, reducing the wavelength still further means what? The energy is increased. When the energy is increased, now we will see what happens. Let us have a break at this point. Welcome back at the break. We have been discussing about the photoelectric effect. I told you just now that a metal like cesium exposed to sunlight will be able to give the electrons. So, the photoelectric effect can be observed even using sunlight. I told you again, using ultraviolet light, almost all metals will be able to eject electrons. To illustrate this point or to explain this point still further, what I am trying to show by means of this slide is, I take the case of potassium. You take potassium metal, expose it to light of wavelength 7000 angstrom. This light is not having sufficient energy to extricate the electron, or the electron could not be ejected by this radiation having a wavelength 7000 angstrom. 7000 angstrom means you are in the violet region, right. So, the electron is not coming out, no electrons are coming out, right. On the other hand, when you come to this range, what is this range? This is nothing but shown in green, right. You know 5461 angstrom unit in the mercury vapor lamp, your green line, you would have done the experiment in the laboratory, the wavelength is 5461 angstrom unit, right. So, this 5500 angstrom unit, that is the green line, the green light is able to eject the electron. Now, the velocity with which the electron will be coming out will be 2.96 into 10 to the power of 5 meters per second. On the other hand, if you go to this radiation, you have VIBGYOR, you go to violet, right. You know violet is what, 400 nanometer means for how much, 4000 angstrom. So, visible ranges from 4000 angstroms to 7000 angstroms, this is a visible range, right. Now, for a metal like potassium, which requires 2 electron volt for the electron to be ejected out. For in the case of potassium, you should supply this much energy, 2 electron volt, to extricate the electron. Okay. So, this 4000 angstrom unit corresponds to 3.1 electron volt. So, 3.1 minus 2, because 2 is the energy required. So, you have got energy here 3.1. So, 3.1 minus 2, that is 1.1 eV converted into velocity, the energy converted to momentum or velocity will be here, the velocity will be much greater, 2.96 to 6.22 into 10 to the power of 5 meters per second. So, the point is, potassium plate exposed to light of red line of 7000 angstrom is unable to eject the electron. Green is able to eject the electron, but the velocity is lesser. Blue is able to definitely able to eject the electron, and the energy associated or velocity with which the electron will be coming out, velocity is this much, means what, kinetic energy is larger, half mv square is the kinetic energy, right, it is much larger. So, the electron is coming with a higher kinetic energy when it is exposed to light radiation of this much wavelength, 4000 angstrom unit, that means you are referring to violet, VIBGYOR, right, violet is 4000. Okay. So, therefore, you expose a metal plate with radiations ranging from red to violet, VIBGYOR, violet to red or red to violet, and you see the consequences. So, for all radiations it will not be, the electrons will not be coming out. Let me move to the next slide. I will show in this slide what you observe. Before going through, I will summarize all the laws related to the photoelectric effect a bit later. The diagrams will be much more interesting, it will make you to understand better. So, now I expose the metal plate to some radiation, right. The frequency of light is given here along the x axis, the frequency of the light given along the x axis. If I have got this much frequency, what happens? The kinetic energy associated with the electron is you do not have electron at all, right. Kinetic energy increases linearly with increasing frequency. That means, for this much frequency or this much energy, the photoelectric effect is absent. I showed the slide earlier. For red line, for red light, it is absent. For a green line or a green light, it starts coming. Okay. So, when you increase the frequency, right, when you increase the frequency, you see the photoelectric effect. Not only you see the effect, and now the more important point is the kinetic energy. The kinetic energy is half mv square, or the velocity becomes larger, right, or the kinetic energy becomes larger. What is kinetic energy? It is half mv square, right. So, I showed you in the earlier slide, you see the velocity here is 2.96 for the green. When you increase the frequency or decrease the wavelength from 550 nanometer, you go to what? 400 nanometer. From 550 nanometer, go to 400 decrease the wavelength or increase the frequency. When you increase the frequency, the velocity becomes 2.96, it goes to 6.22. That is what I am showing here once again, right. When you increase the frequency, right, the energy with which the electrons are coming, they become larger and larger. So, the two important things are, you do not get the photoelectric effect when a metal plate is exposed to all kinds of radiations. For red line or red light, it is absent, electrons are not coming out, right. So, there should be a critical frequency, right. For every metal, there should be a critical frequency, that is shown here nu naught. What is nu naught? It is the minimum frequency which should be incident on the metal plate to start the photoelectric effect. Now, let me ask the question, when you are exciting, when you are exposing the sun, the metal plate to a frequency nu naught, what is the energy associated? Kinetic energy associated is 0. It is the kinetic energy axis, right, it is 0 here. When you increase the frequency gradually, the kinetic energy becomes larger. Okay. Increase the frequency, the kinetic energy becomes larger. Okay. So, this is the minimum frequency for which just the electron will be coming out with 0 velocity or 0 kinetic energy. Okay. This is the critical frequency. So, these graphs show it is impossible to have photoelectric effect for all radiations. For this range, the photoelectric effect will be absent. Okay. Second point is, there is a critical frequency for which alone there will be photoelectric effect. Then apart from critical frequency, if you increase the frequency, the velocity with which electrons will be coming out or the kinetic energy with which electrons will be coming out will become larger and larger. Okay. Then let me ask the question, I have been talking about only the frequency. Supposing for this frequency, I will take arbitrary frequency. For this frequency, the kinetic energy, instead of having light of a particular intensity, if I increase the intensity, what will happen? I will show, or experiments which we you saw the experiment setup, the experiments which were conducted showed when you increase the intensity, more number of photoelectrons are coming out. Therefore, these observations that I am showing or shown, they are enunciated, they are made as the so called loss of photoelectric emission. The kinetic energy increases with the increase in frequency, and the light frequency is becoming larger and larger. The electron current is stationary, that means if the intensity is kept constant, the electron current will be the light intensity. What is light intensity? It is the strength of light, right. The more number of more amount of energy is made to be incident, and then the electron current increases. So, the first thing is the frequency which is to which the metal plate is subjected is greater than the critical frequency, which enables the electrons to come out. Not only that, I increase the intensity, as I told you just now, I have light of greater intensity, right. The flux, the density becomes larger, then the current becomes larger. So, the loss, or what are the loss? There is no photoelectric effect for a longer wavelength, there is a critical frequency for which the photoelectric effect is coming into existence. Thereafter, when you increase the frequency, the kinetic energy becomes larger, and again when the intensity of the radiation it will be made larger or more intense light beam is incident on metal plate, the number of photoelectrons which will be coming out will be larger. Now, these are the observations made, they gave rise to the loss of photoelectric effect. Let me now summarize the loss of photoelectric emission, which are as follows. 1. For a given metallic surface, there is a minimum frequency, the critical frequency, right, for which the incident light can eject the photoelectrons out of the metal. The minimum frequency is known as the nu naught, the critical frequency, right. Light of frequency smaller than this particular value cannot eject electrons. That is what I showed you. When you expose sodium, any metal like potassium or sodium below the critical frequency, no matter how long it falls, it can be falling for any length of time. The intensity also may be large, even if the intensity is large, if it is falling, incident beam is incident for a longer time, whatever be the intensity, then no photoelectric effect will be present, photoelectric current will be absent. Light of frequency smaller than this particular value nu naught cannot eject electrons, no matter how long it falls, time does it come into the picture, and again how high is the intensity. The intensity of the light may be much larger, but still the electrons will not be coming out. The third law goes as follows: the number of electrons ejected out, right, depends upon the intensity of the incident light. Thus, the photoelectric current depends upon the intensity of the light, it is directly proportional, right. Light of frequency higher than the critical frequency or threshold frequency ejects electrons with different velocities. Now, these things I showed you much earlier. Then the last one, the last law says the maximum velocity with which an electron is ejected depends upon the frequency of the incident light and not on the intensity of the incident light. Intensity is nothing to do with the kinetic energy or the velocity with which the electron will be coming out. What is the role of the intensity? The intensity, if it is larger, then the number of photoelectrons which will be coming out will be larger. Okay. This is the definition. The threshold frequency is the minimum frequency which can eject an electron out of the metal. Now, these things are coming out of the experimental setup which we had. This is the experimental setup we had, and you change the radiation from ultraviolet to visible light, all kinds of radiations, and vary. Then not only that the frequencies are varied, what is the other thing that is varied? You change the intensity, right. Parameters which are changed, or the frequency is changed to find the critical frequency which will eject electrons. Second thing is, having found the critical frequency, then you increase the intensity of the radiation and try to find out the magnitude of the photoelectric current. Okay. Now, let me summarize the essential points I discussed in this lecture. The summary goes as follows: photoelectric effect is a process in which light incident on the surface of a metal plate ejects electrons. There is a threshold frequency below which no electron will be ejected. The number of electrons ejected is directly proportional to the intensity of the incident light. Einstein, based on quantum theory of radiation, gave the explanation for this phenomenon. For every metal, there is a characteristic work function. Now, the questions are: what is photoelectric effect? What is meant by threshold frequency? How is the above related to work function? State the loss of photoelectric emission. With this, we come to the end of the lecture. This phenomenon, which was accidentally observed by Hertz, it requires proper explanation, and the explanation came from Einstein, which won him the coveted Nobel Prize, the details of which we will see in the next lecture. Thank you.